The tutorial today focuses on the analysis of linear circuits involving energy storage elements, that is inductors and capacitors, under conditions which we refer to as the sinusoidal steady state. Now, that has two implications, that phrase. The first is that the drive of the circuit, the excitation at some point, could be a source or an external drive, the excitation is a sinusoid. And I use that term in general. I don't mean just sine omega t. You understand that by shifting the phase, by writing it as sine omega t plus some phase angle, you can represent sines, cosines, anything in between. The important point is that the drive is a sinusoid. And the steady state part of that description, sinusoidal steady state, refers to the fact that if you are applying a drive and looking at the response, you wait long enough for the transient that may result to disappear. You wait a few time constants. And so you're looking simply at the response to the sinusoid after some time has passed and all transients have died out. Everywhere in such a circuit, the current or voltage will be a sinusoid. Now, it will differ in magnitude and phase, of course, from the exciting sinusoid, but it will be a sinusoid of the same frequency. That is the character of linear circuits. We are dealing here with linear circuits, which are represented by linear differential equations. And if you drive such a system with a sinusoid, the response everywhere in that circuit is a sinusoid. So the subject we're talking about is the behavior of linear networks with energy storage elements after any transients have died away with a sinusoidal excitation. Let me try and illustrate with a sketch. This is a linear network, or a linear circuit. It contains resistors, inductors, and capacitors. And if it has any sources at all, they are dependent sources. Now, we drive this network at some point, a voltage source, a current source, with a signal or a function of the form some multiplier, I'll call it A, cosine omega t. Everywhere in the network, the currents and voltages are cosines, and wherever we choose to look, this is an input, and we look at some output, some chosen voltage or current, that output will also be a sinusoid. It will be of the form cosine omega t plus some angle, which depends on where you look and what the frequency is, and at some amplitude, not A, but B, different from A, of course. The amplitude is B, so it's B cosine omega t plus phi. And this amplitude B and a phase shift phi are typically functions of omega. So we have a sinusoidal excitation, we get a sinusoidal response, the magnitude B and the phase angle phi of that sinusoid, that is the phase angle with respect to the input, are determined by the network and are generally functions of frequency. Now, if we proceed with the differential equations of this network with a sinusoidal input and search by straightforward analysis techniques for the response, that's a perfectly straightforward thing to do. The only problem with it is that it requires considerable use of trigonometric identities. Now, I don't know about you, but from my point of view, messing about with trigonometric identities is never fun. You have to look it up and be sure you got it right and so forth. So instead of doing this with trigonometry, and instead of driving the network with a cosine, a sinusoidal function, we will make use of the Euler equation and drive it with a complex exponential. Now, you remember that the Euler equation says that e to the j omega t equals cosine omega t plus j sine omega t. That's the Euler relationship. This complex number, e to the j omega t, which has a magnitude of 1 and has an angle equal to omega t, that is, if I represent that on a complex plane, this is the real axis, this is the imaginary axis. E to the j omega t is a vector of unit length making an angle of omega t with respect to the positive real axis. So this is a vector which rotates about the origin at constant angular velocity and is of unit length. The Euler equation makes clear that the real part of the complex number, e to the j omega t, is cosine omega t. The imaginary part is sine omega t, but for the purposes of this discussion and all of the work we will do with sinusoidal steady state, we will focus on taking the real part, which, as you see, is the cosine. Now, the utility of this approach is that if we drive the network not with a cosine, not with a sinusoidal time function, a perfectly realizable function, if we drive the network instead with this complex number, e to the j omega t, instead of using trigonometric identities in the solution, one can use plain old garden variety algebra. It is the algebra of complex numbers, to be sure, but that's not much worse than real algebra, real number algebra. So that is the great advantage of using e to the j omega t as an excitation. If we use e to the j omega t as an excitation, just the same network, if I drive this with some number a, e to the j omega t, what we will get out is some different amplitude, a complex number, times e to the j omega t plus some angle phi. Drive it with a complex exponential, get an exponential response, the magnitude and the angle, complex amplitude, and the angle. This is not a complex number, I'm sorry. This is just the magnitude of the complex number, b. The magnitude and the angle depend on frequency. Drive it with a sinusoid, get out a sinusoid of different phase and some magnitude. Drive it with a complex exponential, get out a complex exponential, different magnitude, different phase. The reason this works in a circuit analysis, as a means of circuit analysis, the way either of these approaches work, comes from the fact that if you differentiate or integrate a sinusoid, you get back another sinusoid. And if you differentiate or integrate a complex exponential, you get back the same complex exponential multiplied or divided by j omega. It is that property of sinusoids and of exponentials, complex exponentials, that makes them useful in this analysis. So to summarize again, instead of solving the problem with a real time function as an input, cosine omega t, we solve the problem with an unreal, a complex number time function, e to the j omega t. It is a construct which enables us to solve the problem not using trigonometric functions and trigonometric identities, but using plain vanilla algebra instead. And that is its virtue. So what does that have to do with the real world? The real world doesn't have time functions that look like e to the j omega t. It has ones that look like sine or cosine. The connection with the real world is to recognize that just as the real part of e to the j omega t is cosine omega t, the real part of the response, b e to the j omega t plus phi, the real part of the response is some number b multiplied by cosine omega t plus phi, just as I indicate up here. And that real part will be identical to what you would get if you went through with sinusoidal functions. Now that identity comes about because the operation of taking a real part of a complex number is itself a linear one. That is, it satisfies the strict definition of linearity that I introduced in one of these some time ago. That's one factor, that the operation of taking a real part is a linear operation. Similarly, all the operations that are involved in solving the differential equation are linear operations. If you multiply the input by a certain scale factor, the output gets multiplied by the same scale factor. If you add together two different inputs, the output becomes the sum of those two different outputs with appropriate scale factors. The differential equations are linear. The operation of taking the real part is linear. And as you know, linear operations commute. That is, I can take a function as an input whose real part is the desired real input, crank it through the analysis, get a function at the output whose real part then becomes the desired time function. It is the linearity of the system we're dealing with and the linearity of the Euler equation that makes this possible. That's the general principle that's involved in the analysis of linear networks under sinusoidal steady-state conditions. Before I move into several examples of how networks behave, let me first talk about the behavior in the sinusoidal steady state of the three passive elements that we're dealing with: resistance, capacitance, and inductance. First, the resistor. Define a terminal current I of t and a terminal voltage V of t, and this is the resistor of value R, or in terms of its conductance, 1 over G. Now, if I let I of t be not a real time function, but some amplitude I, which could be a complex number, e to the j omega t, what is V? Well, V of t is this times R, so it is equal to R I e to the j omega t. V of t obviously is in the form some multiplier times e to the j omega t. If I write that multiplier as V, a complex number, e to the j omega t, where V is just R times I, then the ratio V over I is equal to R, the resistance. So if I excite a resistor with a complex exponential, or equivalently a sinusoidal time function, I get a complex exponential or sinusoidal time function for the voltage, and the coefficient thing I multiply the current by to get the voltage is just the resistance. Or if I turn it upside down, drive it instead with a voltage, and want to calculate the current, I can calculate I over V, and that's equal to 1 over R equals the conductance G. So for a resistor, not surprisingly, since all it does is multiply whatever the current is to give you the voltage, Ohm's law, for the resistor, any time function at the input gets replicated at the output, and the only difference is a scale factor, which is in fact the resistance, or if you're looking at the reciprocal of that relationship, the conductance. Not such a big surprise. Now let's look at a capacitor. Same definition of terminal variables, associated variables, as we always try to do to keep the sign straight. A current and a voltage, either of which can be regarded as applied and the other as response. This is a capacitor of value C. And as you know, the current voltage relationship of a capacitor is that I equals C dV dt. Differentiation. Now, if I let I of t be, as I did up here, some complex number times e to the j omega t, and substitute that for I end up with I bar e to the j omega t equals c dV by dt. And if V is going to be of the form some complex number V e to the j omega t, as it must be, all the currents and voltages of the sinusoidal excitation or a complex exponential excitation have the same time dependence. If I make that substitution, you see that differentiating dV by dt, if I take the derivative dV by dt, it's V bar, complex amplitude, j omega e to the j omega t. In other words, this equation reduces to I e to the j omega t. This equation reduces to j omega c v, complex number, e to the j omega t. These I can divide out, and I'm left with the relationship that I over V, I, as you see, is generally a complex number, it's complex amplitude, I over V equals j omega c. If I want to look at the reciprocal of that, V over I, both complex numbers, is 1 over j omega c. So the relationship, which is equivalent in the capacitor to the multiplication by R in the resistance, is a differentiation which brings out the 1 over j omega c if I'm talking about V over I. And the relationship is still a linear one, only the coefficient now, instead of being a real number, is a complex number. This relationship, the ratio of the voltage to the current, is called, by convention, the impedance, Z, a complex number. The impedance of this capacitor at frequency omega. This relationship, I over V, the reciprocal of the impedance, equal j omega c, is called, by convention, Y, a complex number, the admittance. So Z is the impedance analogous to resistance for a resistor, and Y, its reciprocal, is the admittance. If you have difficulty keeping these concepts sorted out, think a little about the structure of the word, impedance. I apply a current, it gets impeded by the resistor or the capacitor, or as we'll see in a moment, the inductor. It gets impeded and produces a certain voltage. The ratio of voltage to current is the impedance. It's analogous to resistance for a resistor. Admittance, on the other hand, the ratio of current to voltage, you apply a voltage to a circuit element, it admits a certain current. Current flows through, of course. It admits a certain flow of current. And the ratio of that current to the voltage is the admittance, the reciprocal of the impedance. Let's come back now and look at the last element, the inductor. Time function, the current. You can put the arrow on up here, but it's that way. The voltage V of t, the inductance L, and the relationship of the inductor is that the terminal voltage V equals L di by dt. The time derivative of the current multiplied by the inductance is the terminal voltage. If I go through exactly the same argument that I did for the capacitor, where I computed the current in terms of the voltage using an complex exponential form of the voltage, I end up with j omega L times the complex amplitude of the current I. This then is the complex amplitude of the voltage that we're seeking. So the ratio of the voltage to the current, the ratio of those complex amplitudes is just j omega L. The impedance of an inductor is j omega L. The admittance of an inductor is its reciprocal, 1 over j. Sorry, a little sloppy there. 1 over j omega L. Resistor, capacitor, inductor, each of those elements has a relationship between the complex amplitude of the voltage at the terminals and the current at the terminals, which can be expressed as a complex number. In the case of resistance, it turns out to be purely real. In the case of a capacitor or an inductor, it turns out to be purely imaginary. But the point is, it is a simple function of omega. Let me try and summarize that. And at this point, for convenience, although it has other implications, as we'll see somewhat later, I'm going to write j omega as S. This is a lowercase s. I'm not very good at printing lowercase s's, but just imagine that j omega, wherever it appears, is represented by the complex number S. And let me summarize for resistors, capacitors, and inductors the impedance and the admittance for these elements. Keeping in mind that V and I, complex numbers, are the complex amplitudes of the voltage and the current. Well, for the resistor, Z is just R. For the admittance Y, it's just G equals 1 over Y. For the capacitance, the impedance is 1 over CS, where S equals J omega. And for the admittance, it is CS, that is Y equals CS. Z equals 1 over CS. And for the inductor, the impedance is just LS, J omega L, and the admittance, the corresponding admittance, is 1 over LS. Now, when I come down to circuit analysis, with the implicit assumption that the circuit is being driven by a complex exponential, I can perform the analysis just as I would in a resistive network, representing each of the elements by its corresponding impedance or admittance. Let's look at a couple of examples. We'll take a simple one first, which comprises just a voltage divider. A current divider. Parallel combination of two elements, a conductance, G, and a capacitance. Because these are in parallel, I'm going to write it in terms of its admittance, Y equals CS. The terminal voltage is complex amplitude V. The terminal current is complex amplitude I. And I'd like to know what the admittance is looking in here. That is, if I ask what is the total admittance of this, I want to find, by the process of this analysis, Y sub t, the admittance I see looking into this two-element circuit. And I also want to find the current, we'll call it I sub 1, complex amplitude I sub 1. So the things we're looking for are the input admittance of this network and the current that results in the conductance as a consequence of division between these two elements, a conductance and a capacitance. So these are our unknowns. If this were a resistive network, if this were a network with two resistors, you would not hesitate to write the result. Suppose this is G1 and this is G2. You know that the resistance, the conductance looking in there, G, is just G1 plus G2. Or putting it in terms of resistance, it's R1, R2 over R1 plus R2. And if you ask for the current division ratio, how much of the current goes through G2, it's the ratio G2 over G1 plus G2 is the division ratio. Straightforward. Same story in networks with energy storage. The admittance, Y sub t, looking into this network, complex number, is the sum of the two admittances. That is, it is G plus CS. And the current division ratio, I1 divided by capital I, the current at the terminals, I1 divided by I, is just the conductance in the branch whose current I'm trying to determine, G, divided by the sum of the conductances, G plus CS. So we have a complex amplitude for the admittance and a ratio of complex amplitudes for the current division ratio. This complex number can readily be put in the form of an Euler, of the coefficient in an Euler equation. That complex number, I'm now going to go back to letting S equal J omega. That complex number, this is the sketch on the complex plane of Y, real and imaginary, has a real part of G, an imaginary part of J omega C, and it is this vector. If I put it in polar form, Y sub t equals the magnitude of this vector is the square root of the sum of the squares of the real and imaginary parts. That it is the square root of G squared plus omega C squared. See, I've substituted S equals j omega. The imaginary part is omega c, its square, at an angle e to the j theta, where the tangent of theta is equal to the imaginary part, the magnitude of the imaginary part, omega c over g, the real part. What about the current division ratio? I can express that also, I1 over I, complex amplitudes, in polar form. It is the complex amplitude of the numerator, which is a real number g. So the magnitude of the numerator, which is a real number g, and the magnitude is just g, divided by the numerator expressed in polar form, which I've done here. So it's g divided by the square root, I won't repeat it, e to the j theta, or getting it all into the numerator, it's g divided by the radical times e to the minus j theta. Remember, if I take an exponential from the denominator to the numerator, I change the sign. So here is the complex amplitude, the ratio of complex amplitudes, the current division ratio, if you will, in this circuit, expressed in polar form. Here it is if I put S equals j omega. Here it is in a ratio which is not resolved into polar form. This is the way it comes out directly from the analysis. Okay, but the question was, what is I1? We've solved for y. It's this complex number. What about I1? If we want I1 of t, the time function that corresponds to the complex amplitude I1, then we multiply that complex amplitude, I1 complex number, times e to the j omega t, and take its real part. Take the real part of that complex number. All right, let's do it. I'm taking the real part of I1. I1 is equal to I complex number. Turn back here for a second so you're clear what I'm doing. I'm looking at this ratio of complex amplitudes, multiplying through by this complex amplitude to give me I1 bar. I1 bar is equal to this complex number multiplied by I bar. So it's I bar g over the radical times e to the j omega t. This is the complex I have left out e to the minus j theta. It's the amplitude g divided by the radical times e to the minus j theta. I got to have that in, times e to the j omega t. If I combine these two exponentials, I'm taking the real part of I magnitude, complex amplitude, g over the radical, e to the j omega t minus theta. This, the multiplier, this portion of it, is a real number. I'm assuming here that I bar is the real amplitude of some time function at the terminals. In other words, I of t is equal to I bar. In this case, it's a real number, cosine omega t. You know how to take the real part of this. It's just cosine of j omega t plus phi. This is all the complex portion of it is over in the exponential. So finally, I of t, I1 of t, the current, the actual current that you could look at on a scope or measure with a voltmeter, the real part of this function is the magnitude of I, if it happens to be a complex number. It is not, it's just a real number, times G divided by the radical, square root of G squared plus omega C squared cosine omega C minus theta, where the tangent of theta equals G divided by omega C. Did I get that right? Yes. No, I got it wrong. It's the imaginary part, omega C divided by the real part G. It's just tan theta. So you're back to the real world. You got a time function. And the important point is you got it. You got this time function without messing about with trigonometric identities. All you did was algebra, complex algebra, but that's no sweat. That enabled us to determine the current in one arm of this current divider. Along the way, we represented the complex admittance of that two-element parallel combination. Let's look at a voltage divider. This is example 2. And the circuit I want to look at is a voltage divider with a resistor in the upper arm and an inductor in the lower arm. This is R, this is L. I'm going to drive this with some voltage V of t, which has the form V of t equals amplitude V cosine omega t. And I want to find the voltage across the inductor. That is, I want to know what V sub L of t is. If this were a resistive divider with a resistor in place of the inductor, and if that resistance had a value of R prime, you would write the result down immediately. V sub L divided by V, the voltage ratio, is just R prime divided by R prime plus R. We do exactly the same thing in this circuit with an inductor carrying along the complex arithmetic. So the complex amplitude, remember now V sub L, the result, is going to be of the form some amplitude V sub L times cosine omega t plus an angle, I'll call it phi. We got to determine V sub L and phi. The ratio V sub L is now a complex number because it embodies both the magnitude V sub L and the angle phi. The complex amplitude associated with the voltage V sub L divided by the complex amplitude, which in this case is just real, V, of the input, is, thinking in voltage division terms and recognizing that the impedance of the inductor is Ls, is just Ls divided by R plus Ls. So if we want the time function, what I have to do is express the complex amplitude V sub L in polar form to get it into a form in which I can combine it with e to the j omega t. So I rewrite this as j omega L divided by R plus j omega L, and proceed to put this in polar form. So V sub L amplitude divided by V amplitude is the amplitude of the numerator is omega L. It's omega L. And the angle of the numerator is J. That is, it's e to the j pi over 2. Remember that in the complex plane, a purely imaginary number, this is the imaginary axis, is at 90 degrees to the real axis and corresponds to e to the j pi over 2. This angle is pi over 2. So there's the numerator in polar form. The denominator in polar form, proceeding just as we did in the first example, is the square root of the sum of the squares of the real and imaginary parts, r squared plus omega L squared, e to the j I'll call this phi, but this is a different phi than the one I put up there. It won't turn out to be the same. I'll call it phi prime just to keep that straight. E to the j phi, where tangent of phi equals the imaginary part of the denominator, omega L, divided by the real part. If I excite it now with a cosine, replaced in our analysis by a complex exponential, the voltage V sub L of t is equal to the real part of the ratio V sub L divided by V multiplied by the amplitude of the input V multiplied by e to the j omega t, and that's the time function we're looking for. Okay, I think I can fit it all in here. The real part of this complex number is the magnitude of this ratio. That I've got expressed by omega L over the radical, the magnitude of the numerator, divided by the magnitude of the numerator, multiplied by V. Let me put the V out front. The magnitude of that ratio is omega L over the square root of r squared plus omega L squared. I'm going to write the rest of the complex number. I'm left inside the brackets with a complex number which is e to the j omega t times the result of combining these two angles. So I've got to take the real part. I've got to take the real part of e to the j pi over 2 divided by e to the j phi prime e to the j omega t. When I combine these, the pi over 2 adds to omega t, phi prime subtracts from omega t. So what is in the brackets, I haven't got room here to write the whole expression, but what is in the brackets becomes e to the j omega t plus pi over 2 minus phi prime as the argument of this complex exponential. Take its real part, I get the cosine. Read another page here. V sub L of t. Is that what I called it? V sub L? Yes. V sub L of t equals V, the amplitude of the excitation, times omega L divided by the radical times cosine omega t plus pi over 2 minus phi prime, where phi prime equals the inverse tangent, the angle whose tangent is omega L over r. So back in the real world, a time function which we can measure. Before I go on and do one more example, let's do a kind of sanity check on this and go back to this first circuit. Should have done this when I was back here, and ask if what we got as a time function makes sense. What do I mean by makes sense? Well, there are two things you might look for when you go through algebraic exercises like this. One is, does the time function have the right dimensions? The second is, does it seem to behave properly as you go to the asymptote of low frequencies or high frequencies. We'll see in a moment what I mean by that. Let's look at this time function that we got in the first circuit. Remember that the circuit we were dealing with here was one in which we had a conductance G and a capacitance C, G and C in parallel, and we were looking for the current division ratio between the input current, which had an amplitude of I, that is, was I cosine omega t, and the current through the capacitor, which I called, through the conductance, which I called I sub 1. Does this result make sense in those two senses? Well, here we have some with a dimension of current. Here we have dimension of current, and what we have in the denominator, the square root of the sum of these squares, is clearly has the dimension of conductance. So we got conductance in the numerator, conductance in the denominator. The ratio, G over the radical, therefore is dimensionless. So I've got something which has the dimensions of a current. That's okay. What about the asymptotes? Suppose I let omega c get very, very small. Now the page that I had these relationships on is dropped on the floor. Hold on just a moment. If we look at C, the impedance of a capacitor, remembering S is j omega, and I say, what happens to this impedance as omega gets smaller and smaller and smaller, or equivalently what happens to the admittance as omega gets smaller and smaller? Well, the impedance obviously approaches infinity, and the admittance approaches 0, because this has omega in the numerator, this has omega in the denominator. So if I look at the circuit and say, does that make sense? Let's think about it. As the frequency goes very low, as omega goes to 0, this number gets smaller and smaller, and this angle gets smaller and smaller. Its tangent gets smaller and smaller. So in the limit, as omega goes to 0, this argument is just omega t. This relationship is unity, because as this gets small compared with g squared, I can ignore this, take the square root, it's g over g, and all I have is that all of the current, the current in the conductance is equal to the current that I applied, I. That makes sense, because as this impedance gets higher and higher, the current sharing ratio changes, and more of the current flows through the conductance. If these were two resistors, and I said, how does the current in this resistor change as I make this resistance larger and larger and larger, you wouldn't hesitate to say it gets bigger and bigger. Eventually, when this becomes an open circuit, all of the current is flowing through the conductance. So the sanity check, in terms of dimensions and in terms of asymptote, at the low frequency end at least, checks. Suppose I look as omega becomes very large. Well, this angle approaches pi over 2. The denominator approaches omega c squared. This term becomes dominant compared with g squared. And I'm left with a dimensionless ratio again, which goes down like 1 over omega. That is, in the limit as omega goes to infinity, this portion of the current expression behaves like 1 over omega. Is that what we would expect? Well, look at the circuit. Making omega larger and larger means making the admittance of the capacitor larger and larger. In a resistive analogy, it would be like making this resistance, this conductance larger and larger, the resistance smaller and smaller. And in that case, you probably wouldn't hesitate to say that eventually all the current goes through the least resistive path. Well, in this two-element circuit involving an energy storage element, all the conductance all the current at very high frequencies goes entirely through the capacitor. It has the largest admittance. It gets the lion's share of the current. So it makes sense in those terms. Try the same thing on this circuit. What do we got here? The voltage across the inductor, V sub L, with an excitation that is in real time a sinusoid, and in the imaginary number of complex, in the world of complex numbers, is a complex exponential. The voltage, if I have to go to the next page here to write it, or maybe I'll just write it across the bottom. You know what happens when I take the real part of this. The voltage V sub L of t, the real time function, is just the input voltage amplitude times omega L over the radical times cosine omega t plus pi over 2 minus phi prime. Does that make sense? Well, does it have the right dimensions? It does, because this ratio of omega L to the root of the square root of r squared plus omega L squared is dimensionless, and I've got a multiplier of V out front, so it has the right dimensions. Does it behave properly at the asymptotes? Well, if I let omega L become very small, I go to the limit of low frequencies. This says that the voltage goes to 0. The denominator reduces to R. The numerator is proportional to omega. So at very low frequencies, the voltage vanishes. Its magnitude goes like omega to 0. Does that correspond? Well, remember back to the impedance of the inductor. It varies as j omega L. So as I go to lower and lower frequencies, the impedance of that inductor gets smaller and smaller and smaller until you get to the point where there's no voltage left to cross it. That corresponds to this amplitude factor going to 0. When I get to that point, phi prime, this angle phi prime, which is the tangent of omega L over R, phi prime goes to pi over 2. I'm sorry, goes to 0. Phi prime goes to 0 as omega L gets smaller and smaller, and I'm left just with cosine omega t plus pi over 2. Does that make sense? Well, when you think about it a little more, it does, because however small the impedance of this thing is, it is j omega L. So it has the effect, when it's at very small values, of phase shifting the voltage by 90 degrees. Put in a cosine, get out a sine. So the asymptotes seem to make sense, and the dimensions are okay. One more example. Here it is written out. I should have just turned the page. We checked that the dimensions are okay, that the asymptotes seem intuitively to make sense. One more circuit. This also is a voltage divider. It is a slightly more complex one. 2 resistors and a capacitor. This is R1, R2, and C. And I'm going to apply a voltage here. It's really a time function, okay? It's a sinusoid, which is of the form some voltage amplitude V times cosine omega t, perhaps at some angle. I'm just going to represent it by a complex amplitude V. I'll call it V sub I. And what I'd like to know is what is the voltage, V sub O, that appears at these terminals. If this were a voltage if this capacitor were a resistor, you could write the result down. You'd say that V sub O over V sub I is the parallel combination of these 2 resistors divided by that parallel combination plus R1. Let's do the same thing in terms of the voltage division ratio with the capacitor in there. The ratio V sub O to V sub I is the parallel combination of these impedances. The impedance of the resistor is R2. It's the parallel combination of R2 and 1 over CS divided by that parallel combination, R2, in parallel with 1 over CS plus R1. Just as you would, you do that just as you would for a resistive voltage divider. You combine the 2 arms, the 2 elements in the lower arm into a parallel combination and write it down. To be clear about this, in case there's any doubt, what I mean by R2 in parallel with the impedance of the capacitor, 1 over CS, is the product of those impedances, R2 times 1 over CS, divided by R2 plus 1 over CS. And if I clear the fractions in the denominator, this becomes R2 over R2 CS plus 1. Just multiply numerator and denominator by CS. Takes the 1 over CS out upstairs, leaves me with R2 CS downstairs plus 1. So this is what I mean by the parallel combination, here in its write it down form, and here in a rationalized form. So if I substitute that in this ratio, that is, substitute for the parallel combination, numerator and denominator, I get R2 over R2 CS plus 1, all divided by R2 CS plus 1. Sorry, it's R2 divided by that as the first term of the numerator, plus R1. I apologize for this. I hate to do algebra in public, but there you are. Now, if you rationalize numerator and denominator here by multiplying through by R2 CS plus 1, I'm left upstairs with just R2. And downstairs in this first term, when I multiply through by its denominator, I'm left with R2. And then when I multiply R1 by R2 CS plus 1, I get plus R1 plus R1 R2 CS. So we've got the voltage division ratio of this voltage divider now in a rationalized form, in which the frequency dependence is all in the capacitive term, of course, and appears here in the denominator. The output voltage, V sub L, I'm looking in the end for a time function which corresponds to this complex amplitude. The complex amplitude of the output, V sub 0 bar, is just the complex amplitude of the input, V sub I, multiplied by this ratio, R2 over R1 plus R2 plus R1 R2 CS. Now, to get back to the real world of sinusoidal time functions, I will express this complex number here in a form of a quotient in terms of in polar form. So it's V sub I, which is a real number. That is, we said the input time function here is V sub I cosine omega t. That's a real number times the magnitude of this complex number, and now that you've been through this enough, the magnitude of the numerator is just R2. The magnitude of the denominator is the square root of the sum of the squares of R1 plus R2 squared plus R1 R2 omega R1 R2 omega c, all squared. And I'll take the angle right away up into the denominator. You see what I've done here without even talking about it is to say let s equal j omega. If I want to get back into the real world of times functions, I have to do that. I let s equal j omega. The denominator then is the square root of the sum of the squares of the real and imaginary parts, the imaginary part being R1 R2 omega c, R1 R2 omega c, numerator just R2, and the angle of the denominator, that is, if I look at the complex plane again, all these little diagrams are complex plane. I'm not going to label the axes real and imaginary all the time. This is a complex number, a vector whose real part is R1 plus R2, and whose imaginary part is R1 R2 omega c. So the angle that goes with that, this angle, is the angle theta, the tangent of which is R1 R2 omega c over R1 plus R2. I wrote the E here. I did not write the E to the J theta. And it is minus J theta if I define theta this way, because this complex number is in the denominator, and its angle, if I mean by its angle this, theta, would be e to the plus j theta in the denominator, but when I move it up to the numerator, it's e to the minus j theta. So as the last step in this process, we can write the time function v sub o of t as the real part of the magnitude of the input, v sub I, times the magnitude of the voltage division ratio, R2, over the radical, times e to the minus j theta, where I defined theta on the previous page, times e to the j omega t. And the real part of that, the real part of this complex number, we've got all the complex portion of this now in exponential form, and I can combine those two exponentials to make e to the j parentheses omega t minus theta, close parentheses. So the real part of this is the magnitude of this, v sub I. Had it been a complex number, I would be looking just at its magnitude. I said at the beginning it was a real number, so that's an unnecessary step, if you will. But were it a complex number, I want just its magnitude, and I would incorporate its angle in over here, times R2 over the radical, that's the magnitude of the transfer ratio, times cosine omega t minus theta. Back to the real world. The voltage across the parallel combination of resistor and capacitor is that time function. Let's try the sanity check again. The circuit, to repeat it here, looks like this. And the voltage division ratio I'm talking about is the relationship between V sub I and this voltage, V sub O. We represented them correspondingly by a complex amplitude, turned out to be real, at the input, and a complex amplitude, V sub O, at the output, which I had on this page in this expression. Complex amplitude of the output voltage. Does this make sense in terms of dimensions? Well, again, quick check, dimensionally it's a voltage all right, because I've got a resistance in the numerator here, and downstairs I have things like R squared and two resistances times a capacitance times omega squared. If I look at that relationship, R1, R2, C omega has the dimensions of admittance. The admittance of a capacitor is just J omega C. This has dimensions of admittance, and admittance times a resistance has no dimensions. And admittance times an impedance is dimensionless. So the numerator has a dimension in either term, in both terms fortunately, of a resistance or an impedance. The ratio is dimensionless, and I have the voltage out front, so it has the right dimensions. What about the asymptotic behavior? Got to look at the radical for that. If I go to very low frequencies, this term becomes negligible. It's proportional to omega squared. This term dominates. I can take it outside the radical, and I get R2 over R1 plus R2. Well, does that make sense? At very low frequencies, the impedance of the capacitor, which looks like 1 over J omega C, gets bigger and bigger and bigger. Eventually, as omega approaches 0, this impedance approaches infinity, the corresponding admittance approaches 0, and all I'm left with is a resistive voltage divider. So the output voltage ought to be R2 over R1 plus R2, which is what this reduces to. And the angle for lower and lower omegas goes to 0. So I just get the input voltage, cosine omega t, multiplied by the voltage division ratio. That makes sense. And if we go to larger and larger omegas, the very high omega, this angle approaches pi over 2. This relationship looks like a constant over omega because the R1, R2 omega C term in here dominates. So the whole amplitude factor goes down like 1 over omega and says that the voltage out here, the time function, gets smaller and smaller and smaller as I go to higher and higher frequencies. The impedance of the capacitor varies as the reciprocal of the frequency, 1 over j omega c. So as I get lower to higher and higher frequencies, this impedance gets smaller and smaller and smaller until it dominates this parallel combination. And eventually this voltage vanishes because it is appearing across an element whose impedance is approaching 0. The pi over 2 that comes in the theta results from the fact that the impedance of this thing is 1 over j omega c, and the omega shifts the voltage by 90 degrees. So the sanity checks appear to work out. Enough algebra already. Let me try and summarize what we've said here. Rather than approaching the sinusoidal steady-state analysis of a circuit involving R's and L's and C's and possibly dependent sources, that is a linear circuit, no fixed sources in there. If I had fixed sources, a fixed voltage source or a fixed current source, then the input-output dependence would no longer be linear. But if I have a linear network, R's, L's, and C's, and linearly dependent current sources or voltage sources, dependent sources, instead of looking at the response to a sinusoid directly, which requires differentiating, integrating sinusoids, producing more sinusoids phase shifted, instead of going through the trigonometric identities that process involves, we instead imagine in our heads a kind of thought experiment that the network, instead of being excited with cosine omega t, is excited by e to the j omega t. In both cases, of course, multiplied by some scale factor, a voltage magnitude, a current magnitude, whatever. But you imagine the excitation being e to the j omega t, a complex number. You then replace the elements one by one by their complex impedances. When you get more skilled at this, you can do that in your head. But at the beginning, you may find it useful to write them out. Write out the impedance of the capacitor is 1 over Cs in terms where S equals j omega. The impedance of the inductor is Ls. And when you've written all those impedances, or admittances, whatever's more convenient, then you combine them using complex arithmetic in the same manner you would have combined resistors in a purely resistive network, with or without dependent sources. That's the lovely part about using complex exponentials. You get rid of the trigonometric identities. Integration and differentiation become simply division by or multiplication by j omega L, division by or multiplication by S equals j omega L. You do the complex algebra and arithmetic that's involved, reducing in the end to a complex number expressed in polar form. It's got to be in polar form. Then you multiply that kernel, that complex number, by e to the j omega t, combine the exponential pieces to get e to the j omega t with some phase angle, and take the real part of the whole shebang. Take the real part of e to the j omega t plus or minus some set of angles, whatever, to get back to the real world of cosine e to the same thing. Cosine omega, whatever, omega t plus or minus some angle. That's all there is to it. It sure beats fooling around with trigonometric identities, and it allows you to carry over the intuition you've learned from dealing with resistive networks into the world of networks with energy storage elements whose impedance or admittance depends directly on frequency. Thank you.